Hi guys, thank you for coming. Today we're gonna be sharing a paper that was published a few years ago. Its name is Deep Context End-to-End Contextual Speech Recognition. Um, First of all, I think you guys have to check the paper I have shared before, which name is Listen, Attend, and Spell. LAS. That. And then we can look at this paper. The most significant contribution this paper is contributing is that they are trying to incorporate contextual information dynamically into the recognition process. What does that mean? If you can take a look at their proposed model over here, and you can see that in the figure 1, the left part in the figure 1, you can see it's pretty much the LAS, right? The author, I think the first author is not a speech guy, so he's creating lots of his own terms, something like an audio encoder. You just remove the audio here. The attention part is not, I don't like the attention bit here. I think there's something wrong here, but you get the idea, okay? And if you look at the CLAS model, the only thing that's new is there is a extra encoder, which is called a bias encoder. Bias encoder would generate a extra contextual vector, and the contextual vector together with the original context vector together are going to be fed into the decoder, and the rest part of the same. And how they did this bias encoder, let's take a look at their work. Okay. First of all, I think I'm going to skip the basics of the LAS model, the 2.1 section. And also the second part, on-the-fly rescoring, I think you don't get confused by the work on the fly. The reason they say this is on the fly is because um, they're doing something called shadow fusion in equation number 5. Okay. It's very ad hoc, but it's working. And the reason that they call it on the fly is because this is done in the beam search. Before you reach the final result, this is done at every output of the Y. So they mentioned this on the fly. But obviously, you can see that in the figure 1, because the LLS or the CLAS model would firstly hook all the utterance into the encoder. So the system is not a on-the-fly system or a streaming system. And I don't think there's much point to emphasize the fact that the rescoring is on the fly. Actually, in my personal opinion, I don't think they need to do the on-the-fly rescoring. They can, because they're not doing the streaming recognition, they can do the offline recognition, and the results could be better. And nobody cares about the streaming part that they're discussing here. So basically, I would skip the beginning or end word bias they talk about here, because I don't think this makes too much sense. And also, if you look at the figure two corresponds to the table three, and they achieve such a big gain. I think is all because this strange on the fly settings. I will also skip the section 2.5.2. Let's just focus on the core part of their proposed stuff. Okay. Bias encoder or CLAS. C means contextual. Sorry, I had a small flu. Throat needs water. So you can see how the first they talk about the bias, and they also talk about you can also choose not to have a bias, aka biasless, which means suppose you have the look at the figure here. Let me draw something here so we can get it better. So the bias encoder, you have Z1 to Zn, which are n bias phrases. But you could also have, I think they call that Z and B or Z0. Z means nothing. Could have choose to have a non-biased phrase by setting or getting the proper attention weights. Right? You may ask, wait, how do they choose their uh, bias phrases? I think the author they do not explain things in a sequential order, so I also have to jump back and forth. This is the way they create a bias. Suppose you have a batch size of 32. So there are 32 utterances in a batch. So we say I am John. Yes, 32 utterances. And they set the p keep to be usually to be 0.5, which means half of the utterances are discarded first. Discard 50% of the utterances. Okay. Then you got only 16 utterances left, right? Then what's next is they can randomly pull out phrases from the rest 16 utterances in a uniformly style. Let's see right over here. Okay. So eventually they're gonna end up with 16 phrases. And what else? They say that suppose each phrases can have either just the one word in it or up to an order. I think they set an order to four. That means that the phrases can be as long as the four words. I don't think it's word, it's subwords. No. And I think the last step, I think it's not related to the bias phrases, but I'm gonna explain here because it belongs to the training section, right? So when they have these phrases selected, plus one non-biased phrases, which is empty, right? 17. Okay. They want to add one special symbol in the transcript. Or take the play a song, for example. Play a song, for example. Because suppose this utterance is selected, and by randomly select some subbraces in this utterance, they select the word play as the Z, whatever, maybe Z4, play. Then for this utterance, it has a partial match, right? They're gonna put a bias symbol after a play word. Why they do this? I think they also mentioned that very clearly. It's over here. Because if you take a look at the bias encoder right over here, so the attention weights has to be correctly pull out or emphasize on the Z4. I think the arrow should be going upward. Should be correctly selected or emphasized on Z4 instead of giving too much weight on for other phrases, right? Having the training transcription with this bias would allow the model to be able to correctly learn the attention, or in another word, to update. Remember the backprop, right? So the transcription is almost at the end of the output of the decoder. And this is the encoder, right? Because there's a bias term here. So the backprop or the error they learn at the transcription error, the decoder output would leverage the back propagation all the way to the bias encoder and update the parameters in the encoder such that the attention weight can be properly emphasized on the Z4 input. Okay. Inference. I think this inference part is very intriguing to me. So say you have everything trained, okay? They can come up with a Z or the phrases, some phrases which has never been seen in the training, and we will see that in the experimental section. Okay. I think the equation 6 and 7 are very easy to understand. This is exactly the same as the LAS system. This is the decoder output before passing through the softmax, and this is the softmax to get the attention weights, and this is the weighted sum of the hidden vectors or encoded output to get the contextual vector, right? The only thing that's different is that these attention weight, this encoder output are all done on the extra or auxiliary bias encoder. Let's take a look at the figure 1 again. It's all done right over here. It's not done not here. Although the equation is exactly the same as this one, but later on, CXT and the CZT are concatenated together to get a bigger CT we fed into the decoder. Understand, right? Okay, and then they also talked about another very ad hoc thing, which I do not personally understand very much. They introduced something called a bias conditioning. You can see it's easy to understand. Here is what they do. So suppose you have you decode it up to time t, okay? I think that this shouldn't be used t here, because the output doesn't have any timing labels. But suppose you have a partial decoded results, y smaller than t. Yes, okay. And then you can have a list of bias phrases. Those bias phrases are preset, okay, preset. And then you can also have bias prefixes. What does this mean? So if the PI, the bias prefix, was detected on the partial hypothesis y less than t, okay, then you don't do anything to the attention weight in the bias decoder. But if you do not detect this bias prefix in the partial decoded output, you set the m to be maximum, to be infinity. And you can see here, something minus infinity got to almost zero. Not minus infinity. And when you take the log, the alpha weight became zero, which means you only give attention weights in the bias decoder to the bias phrases which has shown in the partial decoded output. Okay. Why they do this? We will see that in the experimental section. They explained it. This is their experiment. They did it on a fairly large English training set. 12 dB is relatively 12 dB is like office environment, a little bit better than office, I think. And roughly like the office environment, noisy. Test set. They have their Google Speech bread and butter test set, the most important test set, a voice search test set. They also have this dictation test set. I've never seen this dictation test before. I don't know which dictation set they're talking about. And they also artificially created a test set, song, contact, and talk to test set. First of all, you look at the results. They tried contextual CLAS without bias phrases. Well, this is interesting to me. They tried it on the voice search and dictation task. They had a very significant gain on each data set. On this one, they got about 10%, at least 8%, okay, 8%, I think. This one is even bigger. This is almost 20% gain. So what does that mean? That means this is the original encoder. This is the bias encoder. They have trained, okay. This is still the input raw audio, not audio. It's still the raw feature. And what they did here, I think if you look at the inference part, let's take a look. I'm gonna read it to you because I think this is new to most of us. During inference, the user provides system with a sequence of audio feature vector x here, and a set of contextual sequence z, possibly never seen in the training. So I think what they did is that the sequence z, they only provide just one empty symbol. That's what they did. That's my understanding. And then they use this empty symbol to be fed into the bias encoder. And this got be later on be fed into encoder. That's what they did. Correct me if I'm wrong. Yeah. This is why you can see in the test set for the average bias list size for the voice search and dictation task, right over shown here, is not shown at all because they evaluated this with an empty list of phrases inference. Okay. So I think this is interesting to me, but also encourage anyone who have seen the video think himself that why this thing worked so well, because to me it seems that suppose you only fed into the bias encoder with a just a one bias phrase, the attention weight has to be given to this phrase. It almost be 1.0 at all time. And so the bias encoder will generate a output vector. There will be a vector, and the vector won't be all zeros. There should be some vector with some valid numbers. But the only thing I don't understand is why this thing, when this magic vector combined with the encoder's output, this is exactly the same. This part I think is exactly the same as the original encoder's output. But adding this extra magic vector, the decoder's outputs or the quality of the decoder output can be significantly improved in terms of WER. My guess is that during training, the author set the probability. Suppose there are 32 utterances in each batch. They intentionally set half of the batch to use the non-bias or the empty bias phrases as input to the bias encoder. So that means, in other words, the author force the system or the model to learn the case that when the bias encoder is being fed with the empty phrase. So I guess you guys all know what I'm talking. But my question is that why fed an empty phrase as auxiliary input would help? Forgive my grammar, but I think you guys all know what I'm talking about. Okay. Leave it to you guys. I will keep pondering on this. And it also didn't say too much about why this thing works or why it didn't work. I didn't see it. And on the fly, I mentioned this. I will skip this section. And they also showed this one. I think this is they want to demonstrate to us on this artificially generated data set. This is the baseline, LAS baseline. And this is LAS plus OTF. OTF, it means the on the fly rescoring. Right? It's supposed to be better. Um, it's really working well for song and context, but for talk to task, oh, they're working always better than the other two, right? Oh, this is not C class, sorry. The second column is still the baseline plus the rescoring, okay? And then they use the CLAS, okay? Contextual LAS. Remember, but I think they should write the CLAS plus OTF here because I think by default the C class CLAS use the rescoring, okay? And you can see for the song and the context, they're working well. That makes sense. But for the talk to task subtask, it's significantly worse than the last baseline, even worse than the last without OTF. Why? It turns out that the authors did a in-depth analysis of this, and they think the reason was because the number of the distractors are too much. Is too much. You can see if the WER without biasing, this is the baseline, right? But once the number of distractors, this means, let's read this sentence. To better understand the CLAS failure with talk 2, we evaluate CLAS while restricting to phrases that appear in the reference transcript plus n distractors, phrases which are not presented in the transcript, chosen randomly from the completed bias list. Um, First of all, I have a question here. I think when they talk about the reference transcript, I think what they meant is the transcription on the test set. So you may ask, wait, are they when they are using transcript? So excuse me. I wish I can finish this recording. So you might ask me, wait, if they use some biased phrases from the test sets transcripts, would that be considered as something that seeing something on the test set? I think strictly speaking, this shouldn't be allowed if you're doing some strict benchmark. But I think if you're doing you're on the industrial track, you're allowed to do this. You're solving a real problem because if you think about the songs you're playing, that you know what are the songs you're gonna be playing. You have millions of runners in your database, right? You always know the name of the songs, so you can always uh, generate uh, or the actions you're gonna do with the song. Mostly it's a play, stop, pause, replay. Those words are highly are often spoken with high frequencies. So you definitely know these words are gonna be appeared in your um, test set. And also in another aspect, your training set is not uh, completely and overlapped with the test set. Definitely your training set has a lot of play, pause, replay words. So you cannot say I do this because I want to see the test set because your training set and the test set are already overlapped. Okay. So what they're saying that if you compile this reference transcript, you compile this bias phrases with a little amount of distractors, you're gonna be doing better than the system without bias. But if you have too many um, disturbing bias factors or distractors, you can see right over here. I think this is almost more than 1,000 distractors. Okay, your WER is gonna be failing. Um, I have to say I didn't read this section very clearly because it doesn't have a lot of text in it, right? And my question is, why there are so many distractors for the talk to set? um, okay. Um, Anyhow, the author they did try the bias conditioning. What is bias conditioning? Let me remind you. It's this one, okay? Means if the bias a bias phrases if a bias phrase has been seen in the partial result, I give it a normal attention weight. If it doesn't appear in the partial result, I just will suppress it, give it 0 attention weight. In this way, they're capable or they are intended to suppress those distracted factors. Okay, and the results is getting better. Oh, there's CLAS with OTF, and you can see when the condition is being added, um, the result is getting better, and when the rescoring is being added, you get a 5.6, but it's still worse than the original system with the rescoring. I didn't see their explanation on it, and I think this is something unstableness. Right, the word. I like the word unstable. So I think these authors are very frank because they can choose not to present this subset and only present the top two, the first two did subsets, which is called cherry picking. But it's so nice for them to share this information with us, so we know what's the best scenario to apply their algorithm and which scenario we should avoid using their algorithm. Okay, that's it. And I thank you for coming and see you next week.